So we've reached this point. We have this sum that goes to infinity of this exponential, of all these exponential terms, and we'd like to add this all together. How do we actually evaluate this sum? There is no, as far as I know, there's no mathematical expression that lets us evaluate this particular sum. But there's an approximation, it's quite a good approximation that we can make to make this solvable. Because unlike for a sum, if we had, say, an integral of this, e to the minus beta h squared over 8ml squared and x squared, this is something that we could solve. Well, if this is 0. Right? So this integral, and then obviously all this needs to be cubed. This integral is basically a Gaussian integral. This is something that has a definite answer. You could plug this into the Mathematica and get a value out of it, whereas that's not true for the sum. And so if we can say, well, let's take the sum and approximate it as an integral, then we're good. We can actually evaluate that and look it up in a table. Now, I said this is a good approximation, and let's talk a little bit about why and when this approximation is valid, because we're going to look at this again when we look at some other cases. So let's think about these energy levels that we have for our, right, we're adding up a bunch of terms. All these energy levels are very closely spaced together. So let's say we have, there's a figure in your textbook kind of like this. Each of these terms we could think of, right, is going to be some value between 0 and 1. That's sort of the nature of these Boltzmann factors. And they're each going to look something like this, where down here is 0, maybe 1 is up here, and we have our different nx values going in along the x dimension here. And as we go to higher and higher nx, these values will keep decreasing because we're getting to higher and higher energy. And essentially what we're saying is, well, we want to know what's the, if we add up all these bars together. It's very similar to if we approximate this as a continuous function instead of a step function, right? Say that nx can take any value instead of only integers. The area under this curve is basically the same as the area of all these bars added together. And so the fact that these values are very close to each other from one to the next means that making this approximation that nx is continuous instead of discrete is a good approximation. Hopefully my drawing makes sense. You can look at figure 18.1 in your textbook if you want to see a better version of what I have here. The final approximation we have to make that makes a very, very small difference for the translational partition function and is essentially negligible is that this value, right, in the sum, we add up starting at 1, and it's a lot easier to evaluate this integral if we start at 0. That has a specific known solution if it starts at 0 instead of 1. So that's another very small change, right? We're essentially going to ignore or going to add an extra bar that goes back here. But there's a lot of these terms, right? This goes to infinity, and so this makes a very, very small difference to the final value of this integral. And so we can go ahead and make this approximation and take our sum, approximate it as an integral, and we can solve this. So this Gaussian function, we can look this up in a table. The integral from 0 to infinity of e to the minus alpha x squared dx is equal to pi over 4 alpha raised to the 1/2 power. So this is just a known solution for this style of integral. Okay, so we're going to have, right, so everything except for the nx squared, right, all of this stuff is going to end up in our solution here. One thing I'll note is that we have an L here. If we take L cubed, that's equal to our volume, so we're going to end up with a volume at the end of this as well. Okay, so Q trans is equal to 2 pi. Now the 2 comes from, we have a 8 down here and a 4 here, so 8 over 4 is equal to 2. All right, 2 pi times m kbt, that's our beta, divided by h squared, raised to the 3/2 power times volume. And this volume comes from our L squared, which we take the square root of, and then cube, right? Because we cube it up here. All right, and so that is the translational partition function. We can also write this in terms of beta instead of kbt, 2 pi m over beta h squared, raised to the 3/2 power, not L, times v. And so we can take the quantum mechanical particle in a box energy levels that describe the translational motion of particles in a confined space, take those energy levels, and using this approximation that we can take these discrete energy levels and when we add them up, we're instead adding up a continuous function, so we can approximate that as an integral, lets us find a specific value from this particle in a box model that we use for a particle. And this is the translational partition function. And we've seen this before already. We've already done some calculations with it.